Okay, good morning. So today we're talking about the interpolation and extrapolation. Uh, so what's the difference between interpolation and fitting? What you've done in physics lab was fit. Yes. So what's the difference between interpolation and fit?
Point. What's the point? Like you need only 2 points for
No.
with physics we had a function that we launched a match to our point.
Yes.
But now we're taking our
Yeah.
point.
So that's one aspect. Another. We can say that's the answer. So in interpolation, we assume that the given data is correct or exact. Okay, the given data, we are given endpoints with the exact values of the function at these points. Okay, and we're trying, and our purpose in interpolation to try to evaluate or to estimate the value of the function at some specific points in the domain of these points or outside the domain of these points. If it's within the domain, it's called interpolation. If it's outside, it's called extrapolation. In fitting, we know how the function looks like, or we know what is the functional form of the function. For example, we know it's an exponent, or we know that it equals some a multiplied by e to the some c multiplied by x plus b. Okay. We know the function, the functional form of the function, and our sampling points are not exactly or are not necessarily correct. There is some error. Okay, and that's where we use fit. Here in interpolation, we know that the function passes through these points. So we demand that the function that we build, the interpolating function, to pass through these points. So we have endpoints, and the most simple way to build a function is to build a polynomial of order n-1, which is the Lagrange polynomial. And you know, when you have 2 points, you can connect them by a polynomial of order 1. If there are 3 points, so the polynomial is about rounding, and etc. So it's a polynomial of order n-1. And I want, and so how can I build this polynomial? So this is the Lagrange idea. I want to build, for example, a polynomial which is called Lj of x, and I want it to be 1 when x or x equals xj, and I want it to be 0 when x equals xi, which is not the xj. So that's the Lj of x. Okay, I want to build a polynomial that is 1 at some xi or xj here, and it is 0 for the other given points. So what is this polynomial? How can I build this? It's very easy, and there's no other. So what's this polynomial? I take the product going over all the i's from 1 to n, but not j, and multiply x minus xi divided by xj minus xi. Okay? So when x equals xi, which is not the xj, there is some term here in this product which is xi minus xi, and that's 0. So it's a product of some n minus 1 terms, that one of them is 0, so that's 0. So for every x, that is xi, which is not the xj, this is 0. And for the x, which is the xj, we have xj minus xi divided by xj minus xi. All the terms are like this. And of course, any one of these is not 0 because we don't go over the j. So that's 1 when x equals xj and 0 when it's not xj. And if I want to build the polynomial that equals y1 at x1 and equals y2 at x2 and equals y3 at x3, what is the polynomial? You understand what I'm doing? Yes, that's it. So the Lagrange polynomial that I want to build is the sum of the given values I goes from 1 to n. So that's how we build this Lagrange polynomial. And you know, if I have n points, there is one polynomial that has a non-zero, one polynomial of order n minus 1 that has the first coefficient to be not zero. Okay, so that's the polynomial. I write it like this here, but I prefer to show you how I build it. And what's the problem with such a way of building a polynomial?
Can be no.
Yes, you're talking about the error. Yes. Okay, that's the thing that we'll talk about it. But I mean, what's the problem? When we look at the aspect of complexity,
Taking long time.
huh?
Taking long time.
Yes. So if I have a data of n points and I calculate this polynomial, and now I want to improve it. I improve my evaluation of the function at a specific point. Don't forget, at a specific point. Given, I know that I want to evaluate the function at x equals something. If I want to improve this, I might add another point or sampling points or data points. If I add another sample point, I have to recalculate everything here. I have to recalculate every product and then calculate it. If you have the polynomial itself, you have the polynomial itself, and you want to improve it by another one new point, you have to make the calculation from the beginning. So that's one problem. And we solve this problem by implementing what's called the Neville algorithm, and we'll talk about it. But another problem that's mentioned here is the problem of error, estimating the error. Before talking about estimating the error, what do we mean by estimating the error when we talk about interpolation? Right? When we talk about interpolation, what do we mean by estimating the error? Or let's first of all, we don't mean anything. There's no estimation of error, but checking the error. What do we mean by checking the error?
Well, first you might have an error because two different x's might be very close, and then the product will be almost zero when it's not supposed to be.
Okay. I'm asking about the mathematical side of it. Forget that we have computer. Suppose that I can make every calculation as good as I want, as I want. What's the problem a priori with this
Maybe we got polynomials like between some points you're gonna get very steep arches.
Yes, I don't know the function. I don't know anything about the function. For example, if I give you a function, if I measure some particle where its location, and I see that this is the axis of t, and this is the axis of x, and I see that at this t it was here, at this t it was here, at this t it was here, this t it was here, this t it was here, here. So what can you say? Someone can say, it seems to me that it doesn't make any movement. So that's the function. Okay. But maybe it's a harmonic oscillator. Maybe it's like this. Who knows? Okay. So when I do interpolation, I have nothing to do with the issue of estimating the error unless I know something about the function. Okay? If I know something about if I know that this is not an oscillator, okay? So I don't know nothing about the function. So I don't know nothing about the error estimation, but I can check my error in the means of if I add more data and I try to, for example, I try to evaluate the function at this point. Okay, someone told me that this is 0. Someone told me maybe it's an oscillator. I don't know. Doesn't matter. If I add more data for you, does this improve your evaluation or estimation or not? That's the question. So that's the question of checking the error. I go further and further by more and more data, and if my new evaluation is not far from my previous evaluation, and I have to say how much. If it's not so far, so I say, you don't have to tell me more data, that's enough for me, that's the maximum I can get. Maybe the error is 1 million, but that's the maximum that I can get, okay, from your data. Don't add for me another sampling quantity.
Can you explain again the first reason? Why the first reason?
Why is the Lagrange? Yeah. So again, if I add another point, you have to calculate this product again and then multiply every term like this with yi and then make the summation. Okay, so you have to recalculate everything. Okay, so in interpolation, that's what we that's the issue of the error. It's not estimating the error, but it is say how much can I change or improve my try of evaluation or estimation based on more and more data. Okay, so let's see only one example of the Lagrange polynomial. Again, every yi you multiply it by the polynomial that takes this with the same thing. Let's say j here for you to see the. So every yj we multiply it by lj, which is the product of terms like these, which are the x minus xi, except that j divided by that j minus xi. So, for example, before here, this is my data, okay? The function, someone gave me that the function equals exactly 4 at x equals 0, it equals 0 at x equals 1, it equals -2 at x equals 2. So 4 multiplied by x minus 1, x minus 2 divided by the 0 minus 1, the 0 minus 2. Okay? Plus 0 multiplied by it's 0 plus minus 2 multiplied by x minus 0, x minus 1 divided by 2 minus 0, 2 minus 1. Okay? Yes.
We'll always be taking polynomial, or we'll be taking more complex functions. If we have given that.
And interpolation, we only use polynomials right now. Right? And you know, extrapolation is more dangerous than interpolation when the point is not in the range that we are given the data in. So it's we are more likely to be wrong in extrapolation than interpolation. Okay, so the Neville algorithm, what it says, I will make this evaluation step by step, okay? And I will suppose that I will be given every time a part of the information. I will calculate every time based on this calculation my evaluation of the function. So, for example, if you want me to evaluate the function, you give me these 4 points, and you would tell me that at x1 the value of the function is y1, at x2 is the y2, at x3 is y3, at x4 is y4, and you ask me to evaluate the function at some x here between x1 and x2. Okay. I tell you that if I want to use only the information that you gave me at x1, I will evaluate the function at this x that you asked me about as y1. Okay? If I want to use only that piece of information. Only. If I want to use the information that you gave me about x1 and x2, okay, I will use the polynomial p12, which is built of p1 and p2. Again, if I want to use only the piece of information about x4 that you gave me, in order to evaluate at this x, I will say that my evaluation at x is y4. Okay? But if I want to use x3 and x4, in order to evaluate here, this is extrapolation, I will say that my answer is p34, which is built of these two. We will say how we build it. Okay. If I want to use 2 and 3 and 4 in order to evaluate O, I will use P234, which is built from P23 and P34, which are the polynomial. This is the polynomial that evaluates here based on the data of x2 and x3. And this is the polynomial that evaluates here, which is based on the data from x3 and x. And the last one, P1234, will be the polynomial that evaluates here based on x1, x2, x3, and y1, y2, y1. So this polynomial at the end will be what? This at the end of the process. Yes, but we know what it is. It's the Lagrange polynomial. It will be the Lagrange polynomial. But if you add for me another piece of information, I will somehow only calculate P5, which is given. I will calculate P45, this, and P1, 2, 3, 4, 5. So I don't make use again of all these. I use something that it's already there. So in terms of complexity is less, but in terms of memory, it's more. Yes.
What do you mean when you say the polynomial that evaluates here, it's what? So the polynomial value is in what?
Between, I have some point here between x1 and x2. And I want to evaluate that.
Why between one and exterior, not between.
It's an example. It's an example. But what I want to say, you have to fix what do you want to evaluate and make this possible. Because we will talk about it. Okay. Another question?
If you add another point in the middle, or have the same process, then you make
Here? If I change my sampling intervals. No, you will make it, you will recalculate it. Okay. How do I build this polynomial from the polynomials before? It's somehow it goes with the same idea. I want for example, I want to build this from these two. If I take this, which take care of x2 and x3, I want that when x equals x4, I want that this does not I want this not to be counted. I want this. So I want this to be multiplied by 0. So I build this as x minus x4 multiplied by this minus x minus x2 multiplied by this. It's in the same way that I built that, but we can think about it a little more. Divided by x2 minus x4. Okay. So the formula for building some polynomial from the two before is like, it goes like this, but it's also what I said, and I now gave you a more complicated example than this, but you can look at this. P1, if I want to build this, I multiply P1 by x minus x2 minus P2 multiplied by x minus x1. I say minus x minus x1. Okay, it's the same. Divided by x1 minus x2. Okay. And you, again, what I've just said already proves for you that this takes in account this and this and make the correction for x1 and x3. But again, because we are in a mathematical course, one should prove that the end of this process gives me the Lagrange polynomial, and the proof of this goes like what? Goes by induction. Okay, so you can prove by induction that the end of the Wheel algorithm gives you a Lagrange polynomial, the Lagrange polynomial, the known Lagrange polynomial. Okay, and now again, if I and now here why I told you to fix something. If I evaluate the polynomial at some x here, the question to be asked is, okay, you at first said to me that it's P1. After that, you used also x2 and said to me it's P1 too. And after that, you used the information of x3 and told me the answer is like this. And then you used x4. So if this is 1, let's say that the number here is 1, and here I get 1.01, and here I get 1.005. So I somehow see that my improvement is only changing, for example, in the third decimal point, in the third decimal digit after the point. So if it's enough for me, I can say to you, okay, don't add for me x5 and x6. I don't need them because I see that there is no improvement other than changing the third digit after the point. Okay. And it will be enough for me. So maybe I will use maybe another person will use only P1, 2, 3. It's enough for him up to the second digit after the decimal point. But that when he calculates here. But if he calculates here, maybe he would use P2 to 12. Okay. So there is a question always, which points do I have to take, or it's enough for me to? And this question is always dependent on the value itself. Where do you want to evaluate the function? And let's say that if we evaluate here, somebody says for us, okay, I will start with 4. Okay. And then I will improve my 4 to P34. And then I will improve it to P234. We expect that this would be better than this, but maybe not. Maybe this is better for some function. And we don't, because we don't know the function itself.
What do you mean by better?
By better, I mean that the value doesn't change so much when we use more and more points. Okay, and that's the maximum that I can get. So always we have the question at a given point, do I want to add more points from above or more points from below? Okay, and the question about points from below will be answered by the differences in this line. Okay, and the question of whether to add points from above will be answered by the differences in this line. Okay, so these differences I call them the C's, and these differences I call them the D's. Okay. So that's the C's, that's the D's, and let's see an example of this. I have x1, x2, x3, x4, x5, and someone told me that the function at x1 is like this, at x2 is like this. This is the depth. And we are trying, we have finished our evaluation, and that's the result. We are trying to evaluate the function at 0.15. Okay. So if we use only the information that someone gave us about x5, we would say the answer is 0.45.
The value of the function.
The value, if I told you that the function at x5 is like this, and I ask you about some another x, what's the best that can you do? Okay. And if we use x4 and x5 and want to evaluate here, the answer is like this. Okay.
It's supposed to be a polynomial.
Huh?
Isn't it supposed to be a polynomial?
Polynomial evaluated at
What's the answer? Can you show again?
here minus 0.7.
That's the answer for x.
That's yes. Everything here is an evaluation of the function at this point. Okay. And now let's see. If I use these two and get this, I call this extrapolation because I'm asking about a point which is outside the domain I use the data in. Okay. If I use x2, x3, x4, x5 to evaluate 0.15, the answer is this. And again, it is an extrapolation. Only when I use x1 combined with them, it's an interpolation. And let's see what goes when we use x1 and x2 That's the answer. And when we use x3 combined with them, that's the answer. And x4 and x5. And you see that this difference is 0.4, for example. This difference is 0.04, and this difference is 0.001, okay? And this difference is 0.005. So we are changing. If we add more and more data from above, it's below here, but these points are above x. If we add more points from above, it seems that our answer would change only in the third decimal digit after the decimal point. So we can say it's enough for us. And we can ask also about points below. Okay, so for example, when we start here to evaluate here, if we added points below, these are the D's, you see that the D's are much bigger because we are extrapolating. Okay.
So in this case, if we wanted to add more points, we add x6 or x0.
I didn't try zero until now. I don't know. Maybe x0 would not also help me. That's it. For this point.
The best answer is the one that in the far right or in the second row. Like, what is the best answer?
The best answer I can get, I can try more points, and I will say that the answer is this plus minus 0.005, and that's the maximum I can get.
Minus 1 point.
But maybe the answer is 1 million. Okay, I don't know.
If I would take a symmetrical value,
Also, I don't know, because maybe the function is not symmetric. We'll see something like this. We'll see now a symmetric function, which is x squared, that if we sample it in some region, it would ruin some another region. That's because we know that the function is symmetric, but maybe another function is not symmetric, and it really goes somehow wildly in some side of it, and maybe it's better to have a sampling method in one side and another sampling method in another side. If we don't know anything about the function, we don't know anything about the error. Okay, so that's the best that we can do. Okay, so we talked about the errors, and here the example. Suppose that the real function is x squared, but we don't know that it is x squared. Okay, someone told us that the value of the function at -1 is 1, at 0 is 0, at 1 is 1, and use the Lagrange polynomial to interpolate the function, for example, for a point here. The answer is we know that there is only one quadratic function that goes through these points, and that's the x squared. Okay. And my interpolation here is x squared, and my interpolation here is x squared. Okay. Now suppose that he gives us also another 10 points here. 10 points here. What do you expect to be? Huh?
X squared.
No. That's the answer. Okay. Okay. That's the answer. Because I told the computer to compute for me. Why the Lagrange, the Neville algorithm or Lagrange polynomial? To compute for me a polynomial of order 12. And I told him how to compute this. such that it goes through these points and this point and this point. Okay. Now, when I told him to go through these points, okay, the real answer would be for all the efficients to be set to 0, except this one should be set to 1. Okay. But what he makes now, he makes a polynomial of order 12, such that these corrections to the x squared. Okay, so what is this function? It is x squared plus a correction when this is 0 point. Okay, let's call it like this. So this correction at these points is exactly 0. These powers exactly cancel out somehow. But in the right side, these powers, the odd ones, change change sign, and then it goes widely like this, or we have a big oscillations like this. Okay, so this is a problem. So I can reformulate or restate my statement like this. When you told me about these 3 points, I managed to interpolate the function successfully somehow, but here in this region. But when I want to interpolate here in this region, and you added for me these points, when you added these points, you ruined for me my interpolation here.
I think there's a secondary effect happening here in the graphic shown, because a 12th order polynomial is not supposed to look like that. There's too many features. I think the interpolation of matplotlib or whatever you're using here,
Yeah,
additional features.
of course, there are many errors here. For example, this. Yes.
Yeah, like that's not.
Yes, yes.
That's an additional feature of the graphic software.
I understand. Yes, there are more. He says that this is not this is not a polynomial of 12 of order 12. You see, because you see many things like this. A polynomial of order 12. What do we know about it from calculus?
Has 11 stable points.
Has
11.
no, it's something more simple. It has maximum. How many points of maxima and minima? Maximum.
Maximum is 6.
11. Maximum and minimum. It's yes. Okay. So a quadratic function. It has maximum 1 point of minimum or maximum. Cubic function, it has maximum 2 points of minimum and maximum. So we should have maximum 11 points of maximum and minimum. And you see here, there are many maximas here, yeah, for example. So it of course not the polynomial itself. Yes, there are more errors that are added, but here we of course see oscillations. Okay, and the computer did not compute this well. That's it. So when we added more points in some region, we ruined another region. And somehow we should know how to sample the function if we know an information about it. Okay. So here another example. And when so the function is this absolute value. And if we have 3 points, we will give this parabola. And if we have more data, here we interpolate somehow successfully. And of course, the black line is not exactly on or lies on the red line, but here we have the oscillations because we told the computer to cancel out each of the exponents of the high order exponents or powers here. So here we have the oscillations, and this is a big oscillation, as you see. So that's a problem in this interpolation. We should, and here we see symmetric functions. Maybe the function itself is like this. Maybe. So we succeed. So the issue is somehow we need to know something about the function in order to say our interpolation is good or not. Okay. In some form. So if we want to interpolate here, it seems that we should take points here and less points in another range. Okay. Questions? Okay. So this is a note for you to know that the fitting or the fit is somehow to fit. We just talk about this. We have data. This data has some errors, and we want, for example, we know that the function is linear, so we tell the computer the function has to be ax plus b, but which a and which b will the computer choose? The answer is also we tell the computer that we want the function somehow to be as close as to these points. Okay, but what's the meaning of as close as? So we have to give some function to measure or to quantify some global error of our fitting far from how much it is far from the data. Okay, so that's called the metric. And the famous metric that you use in physics lab is what's called the chi-squared, or the minimal mean squared errors. So you somehow assume that the errors in all of your data are the same error. Yes? And you want your line, for example, if it's linear, but it can be parabolic or exponent, you want it to be far from the data as minimum as you can. What is the minimum, or what is the function that I calculate the minimum for it? I calculate the error between the function and between the data that I measured, and make the square root and add all these errors. Okay, so that's the sum of the squares of errors. Is this? So this is the measured one, and this is the estimated one. The estimated by your estimation function or fitting function, and we don't call it interpolating function. Okay. So that's a way of interpolating. And question to be asked, can we do better? Always we can do better. And this is, we'll talk now about the spline interpolation. We'll talk about the cubic spline. You can use more than cubic. Let's talk about it. So here we have in the cubic spline interpolation, when we have a data of n points, we match for each segment a low order degree polynomial. For example, if I have 100 points, I choose to for this polynomial here only in this segment to be of order 4, for example, or 5. Okay, but in each segment I have another polynomial. All of them are of the same order. Okay, I call this S1, S2, S3, up to Sn minus 1. And this S1, for example, is A1 x cubed plus B1 x squared plus C1 x plus D1. This S2 is A2 x cubed plus B2 x squared plus C2 plus D2. Okay? So every segment is a polynomial. And of course, I want that Si at xi to be equal to yi. S1 at this point, I want it to be y1. And I want Si at xi plus 1 to be yi plus 1. S1 at x2 is x2. Also, S2 at x2 is 2. Okay? So how many parameters do we have in this interpolating function? So this is a smooth piecewise interpolating function. In each segment, it is smooth, but when we change from when we move from a segment to another segment by the point of the data, we will have some derivative of this total function, which will not be continuous. Okay. So how many parameters do we have in this interpolating function? Huh?
N minus 1 times 4.
Yes, so 4 for each s, and we have n minus 1 s's. So we have the hope that this interpolating function will be better than the Lagrange. Why? Because in the Lagrange interpolating function we used n parameters that we found, and here we use more parameters. So we hope that this interpolation is better.
But the calculate now is more complicated as well.
Yes, yes, but the function is more is better. So you have to determine what you want or to decide. Okay, so in order to determine these,
The big advantage to this form is that if we add a point, we only have to change, like remove one line and add two small lines, right?
yes,
So it's much easier to modify this.
yes,
But if you want to move a dot, it doesn't propagate.
yeah.
That's the thing.
If I saw, for example, if I know that I will use another point here, I will solve the equations here. And when you add points, I change only the Sn minus 1 and the Sn. Okay. So for your question, I always solve for these and make these with parameters, so that if I want to modify this or to adjust this, it doesn't cost me so much.
Why in this example, if you had another sampling point, then you need to change the Sn minus 1 cubic time.
I will explain now. You will see it. So how many constraints or conditions are here? 2 times n minus 1. Okay. So I also have to impose more conditions to determine these 4 times n minus 1 parameters. And my conditions, because we are in physics, we like, and that's why we chose cubic, we like the second derivatives to be continuous. So we also demand that the first derivatives here are continuous and the second derivative. So we demand that SI tag at xi plus 1 equals SI plus 1 tag at xi plus 1. Okay, there, tag. Okay. That's the first derivative, and the second derivative also to be continuous. Okay. And how many constraints are there here? You see, we have n minus 1 polynomials. They are connected by n minus 2 points in between them. Yes? So we have 2 times n minus 2. The 2 is because this is 2, and for every I goes from somehow 1 to n minus 2. Okay?
N minus two.
Huh?
Why is n minus two? But n minus one.
Because we don't take these 2 points, yes? Only these points we have, okay? So you can say that I here goes from 1 to n minus 2. I goes from 1 to n minus 2. So we have another 2 conditions that we have to impose in order to have a solution. Yes? And that condition will be something that we know or we assume. Okay. For example, if physically we know that the derivative of the function at the endpoints is 0, we impose them. We say that S1 tag at this point is 0, and Sn minus 1 at this point tag is 0. If we don't know anything, a reasonable thing to do is to say that the second derivative here is 0, and the second derivative here is 0. Why it's reasonable? Because that we don't know another information, and the information is only from here, we assume somehow that in the near region or the surrounding of this point, the function is at most is linear. That what means that that is here. Okay. So again, it's something that we know about the problem or we assume. And the question to be asked here, why is this better than the Lagrange way? We hope that it's better. So one thing, it doesn't have that oscillations, because you see, we use only low order polynomials in the region. Okay, so we don't have the problem of oscillations, and especially the oscillations that are called Runge oscillations that are near the endpoints. They are in the Lagrange polynomial. We have here much more oscillations than in between, and it's like the Gibbs oscillations. You know them in Fourier transform. Okay, so this way of the spline interpolating method avoids these oscillations that we've seen, and also it is better in the means of the error. How we improve ourselves or our polynomials when we add more and more points. So that's for now. Let's take a break and then take an example. Okay, so okay, that's maybe I should have used this. Okay, and let's see an example. So we know about some function that we know that at -1, at 0, 1, 2, at -1 it equals 3, at 0 it equals -1, and at 2 it equals 3. So we want to connect these 3 points by S1 and S2 somehow. And the S1 is A x cubed plus B x squared plus CX plus D. And the S2 is E x cubed plus F x squared plus G x plus H. Okay. And first of all, we want that S1 at -1 will be 3. And at 0, it will be -1. And also we want S2 at 0 to be -1. And we want S2 at 2 to be 3. Okay? So these are 4 conditions. And of course, we start with the 0, because if we want to solve this, it's much easier to start with the 0, because in a polynomial, when you plug in 0, you have all the coefficients 0 except the free one. So we want that at 0, the function will be -1. The two functions will be -1, the S1 and the S2. So D and H are -1. Okay. And if we plug in -1 in the formula, we get this, and we want to be 3. And this formula, we plug in 2, and this will be the answer, and we want it to be 3. So we have H equals D equals -1. These are 2 equations, about 2 simple equations that we know what are the D and H from them. And we have another 2 equations, and now we want the derivatives to be at 0 to be equal. Okay, so that's also easy, because if I want the derivative at 0 to be equal, that means that the G equals the C, because we plug in 0 in the X. And if I want the second derivative also to be continuous, that means that the F equals B. Okay, and we have now more than this, another 2 conditions that are the second derivative here and the second derivative here. And then we solve these equations. These are linear equations, not a problem. We solve them, and this is the answer. Okay.
I think the second derivative of the x's should be equal.
Not equal. Equals 0. Again, that's a condition that I impose from my head, because I assume that, because I don't know anything about the function, I have to impose some condition, and I choose this condition to be that the function here behaves linearly, near to the function, near to the point. Okay. So, and this is another note for you to know. If you have a data of n points, and the value of the function at these n points, and the value of the derivative of these n points. For example, if you know the location of a particle and its velocity, or speed, okay? So that's the function of the derivative. So there is a closed formula for interpolating this by a polynomial, and we use in this method what's called Hermite polynomials. Do you know them? Okay, so you will know them. I hope, because this semester is 10 weeks. In the other semester, you will meet them in quantum physics. I hope you did them. These are known polynomials, and we use them, and we have a closed formula for the interpolating function using them. So that's it. That's it for you to know. And the way that we make the interpolation using the spline is the enter P1D. Okay. Now let's talk about multidimensional interpolation, which you didn't talk about the lecture. So suppose that I have a grid of x's and y's and the value of a function of at these x's and y's. So suppose that we have a scalar function that depends on two variables, two arguments, x and y. Okay, it's a scalar function, but it gets two arguments or two variables, x and y, and we have sampling points in this function of this function for some x, x1, x2, x3 up to xn, and y1, y2, y3 up to ym, for example. And we want to interpolate the function in some point between in this range, not one of these points, but in this range. Okay, so we have a scalar function, and we somehow want to do an interpolation for two variables. Okay, so how do we do this? The answer is we do the interpolation for one axis many times when we fix the another variable, and then we interpolate these results in the second axis. Okay, so what do we mean? We will make now the very simple or the most simple example. If we have only these points, okay, so suppose this is called x1, x2, and this is y1, y2, okay, and only from these points I want to interpolate the value, the function here. I want to evaluate the function in this point for some example. So we have f of x1, y1, it's given to be f1, and f of x2, y1, it's given f2. This is a value that it's given, and f at x2 and y1, it is f4, I think. X1, y2. Yes, 4. And f at x2, y2 is f2. Okay. So the way is to interpolate the function only at this line. Okay. So I will say that f of x at this fixed yj is a linear function here. Okay. And I will have some function, some linear function of x. That's here. Here I will say, I will interpolate the function f of x at the fixed yj plus 1 or y2 to be the, I will interpolate the function here, okay? So it will be a linear function of x, another linear function, okay? And now I have a function here at y1, and I have another function at y2, and now I interpolate these two functions in the y-axis. In the same way, also it will be linear in these two f's. Okay. So let's say how we do this. Here, at this line, I will say that f of x, f of x at y1, okay, is linear. How do I build a linear function of this? These two? I say that f of x at y1, for example, minus f1 equals f2 minus f1, x2 minus x1, x minus x1.
It's not supposed to be zero.
Huh?
It's not supposed to be zero.
What's supposed to be zero?
F should x1 y1 minus f1.
What? Okay. So again, we have fixed y1, and that's how we make this interpolation at y1. So that's how we make the linear thing. Okay, so the function is f1 plus this. So this is the thing that you know, I think, from high school, but we can make a little bit massage for this in order to see that this is exactly also the Lagrange polynomial. Yeah? This is the Lagrange polynomial of 2 points. Okay. That's for you to know or to see that or to check that. It's enough up to him. And now from these two, I will get what? I will get f, another interpolation function, another function at y2, which is, let's say, minus f4 equals f3 minus f4 x2 minus x1 x minus x1. Okay. So this function is a linear function. At x1 it equals f4, you can check that. And at x2 it equals f3, you can check that. Okay. This is a linear function at y1, which is at x1 it equals to f1, and at x2 it equals to f2. Now I will make the interpolation between these two functions along the y-axis. How do I do that? I have that. You can forget about the x here. You can forget about it. You have some function of y1 equals some value. This value is a function of x. And some function, the same function at y2 equals another value, which is another function of x. But you can forget about this thing that is the function of x. Now I want to interpolate these two things, and I want to say this function of y is linear in y with these values of the x. Okay, so f of x, y, it's the same linear interpolation. F of xy minus the value at, for example, y1. Okay. Yes. Equals multiplied y minus y1 the value at y2 minus the value at y1 y2 sorry, y2 minus y1 the value at y2 minus the value at y1. Okay. Now this function f of xy, when y equals y1, when y equals y1, it is f of xy1 that we found. And this function at y2 is f of xy. Okay? So the f of xy is an interpolation function of these four, this grid of four data or given points. And I can ask now what is the answer at xy and plug in the value of x and y. Okay, and this function, what its shape or functional form? How does it look like? What terms in it?
X equals constant.
Hmm?
If X equals a constant.
No, what terms in this function do we have? We have the term of x multiplied by y, x1, x times y. And we have x, and we have y, and we have a constant. That's it. You see that? Okay. And it is also somehow expected that we have four parameters. Why? But we have four given points, four conditions to impose on these parameters to determine them. Okay, or to find them. So that's the interpolating function, but remember that we did only linear because we had 2 points. What if we have a grid? Again, we use interpolation function along one axis, and this will be a polynomial, not a linear one. But the idea, I think that you learned this idea now or understood it, that I make the interpolation, I make another interpolation, and then make a polynomial of these polynomials. Each one is a polynomial of x, and now I make a polynomial of y built of these polynomials of x. Okay? So the answer will be something that you expect. For example, here I expect that I get xy and x and y and a constant. And a nice question that was in the previous recitation, someone asked me, what if I have a grid of points that are not ordered in the axis? That's the given data that I have. I have the value of the function at this point and at this point and at this point, at this point. So I don't have this interpolating method of use. Okay, so what's your answer for this?
Now, transformation to a base that is
No. We know what transformation?
you do a linear transformation to a base in which the axes are like more aligned with the points. When the points are in a line that you remove the base, you make kind of the same.
Okay, so somehow, yes. It's here. So also here I want to guess somehow the polynomial that I want to get. Okay, and the polynomial that I want to get, for example, let's say that it's based on all these, and based on the number of these, I will say that the polynomial is x to the power of multiplied by y to the power of plus x to the power of multiplied, and I have many coefficients, and I have to find these coefficients. Okay, the difference between that case and this case is that I have to solve all these equations here, and it is a net of coupled equations. But when I have the data ordered, I can solve the whole problem by dividing it to smaller ones, and the complexity of the solution is much lower. And I make the interpolation here, 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 and then I make the interpolation between all the interpolating functions at one axis. Okay, there was a question here.
Really understand the drawing of like the grids there. What does it mean that for one X I have two Y's? What's the shape of it?
Again.
I didn't understand. What does it mean that for like XI I have two F's, like F1 and F2 for Y.
Okay. So you have a two-dimensional world here, and you have a function on this world. For example, the temperature at this point, the temperature at this point, the temperature at this point. Okay, so at this point, the temperature is given to be F1, and at this point, the temperature is given to be F2. It's a function, it's a scalar function of a two-dimensional world. Okay.
Can you explain again what you're talking about? All the points aligned, how it's easier?
It's only a note. It's easier because I can, if I ask you to solve this problem by not this way, by telling you that the function that you are interpolating it will be axy plus bx plus cy plus d. Okay?
Yeah.
And find the ABCD. It's easy. Okay. You plug in x1, y2 and say that this should be equal to f1, and again with the other values, and you have four equations for the four coefficients, and you find them. Okay. But we found them in a much easier way, because I know that this polynomial will be the result of the interpolating polynomials at each axis and then interpolating. And this is much easier. In the linear case, maybe you see that they are the same or equivalent, but if we are talking about 10 points that I want to interpolate to polynomial of order 9, that's a hard question if I use the 81 points at once and solve 81 equations. Coupled equations. And the other way, I solve 9 coupled equations, 9 coupled equations, and 9 coupled equations. And after that, I solve 9 coupled equations, but not 81 coupled equations. That's much harder. Okay, so here we have the definition of T and U, especially for this example, it's not so important. What's important that you understand how we make this interpolation in more than one dimension. And now notes for the NumPy. Okay, I understood that the polyfit now is called NumPy, called polynomial fits with dots, I think. You should check that but in Google or something, but the function of the fits at NumPy is called now polynomial dot fit. Okay. I hope that I'm not wrong. You can check that. And let's see, for example, when we talk about, so let's read what they want. Write a code that performs polynomial interpolation for the function f of x equals the absolute value of x and the domain -3 up to 3. where n equals 8 points are known at equal intervals, and after that for 1000 points, and use these functions, okay? So if you want from -3 to 3 with equal intervals or segments, which are 8, for example, so you get 9 points. So you can use this command, linspace, okay? And you can use the functions to make the fits or the interpolations, and that's you should check. I should not you. I should correct here the colors because there are here 6 functions and 4 colors, and because of this this is 1. So the orange one is the real function. Okay, that's the absolute value, and the dots, of course, are the the sampling points, and then you see the interpolating functions and the fitting functions. For example, the red one, what do you think about it? Is it an interpolating function or a fitting function? The red one, it's fitting because it doesn't pass through the points. Okay. And also here you have an example of implementation of the Neville algorithm. So Neville algorithm, you want to give it the vector of x, the vector of y, the values at these x's, and the x value that you want to approximate the function at, okay, or to evaluate or to estimate the function at. And how do we build it? You know, because of that triangle grid, let's call it. It's a loop in a loop. But in this implementation, you see it's not easy to add a point to this Neville algorithm. So it's only the Neville algorithm implementation, but not an implementation that permits you to add points without a complexity loss. Okay? So that's for you to see only. Okay, so only we also we finished early. The next week, you know, if we will have an exercise or homework or not. We'll have a recitation, but homework. You're sure?
Yeah.
Okay, so no homework next week. They decided, not me.
And in the next week's too, for sure.
Well, we will have recitation, but we will be in Dan David 303. There, the audio will be much better in the recordings.